Okay, so here is part 2 of, probably this will be the last part, but part 2 of videos about the technique of u-substitution for working through integrals. Okay, so anyway, in my last video, let me see, how can I say this? I tried to introduce a lot of the terminology. I gave a lot of the formulas and so on that we will be using. And in this video, I'm just going to work problems. So my point is, in the last video, I tried to do a lot of explaining about why everything works the way it does. And that might not be for you. Maybe you just want to get down to business and see what you're supposed to do and not think about it. And I'm not really trying to be harsh or insulting when I say that, but not everybody cares about all the details, and they just want to know how to get things done. Now, I think that you should definitely know how to get things done, and you should understand the details. That'd be the point of taking the class, but I guess it's not absolutely required. So in this video, all right, we'll just get down to business and figure out how to work the problems. Now, let's look at, I don't know, I thought it would be good to give an outline of the method, okay? So with the first problem I'm going to do is over here. It's this one, okay? And what is the method for doing that? Well, okay, so here's what we do. We choose a substitution for u. U will be some formula that involves x that you choose based on your understanding of how to do this. You calculate du as f prime x dx, and then you substitute that into the integral in a way that the integral then only involves the variable u. We may have to use a little bit of algebra on these in order to get the substitution to work, but that's the goal, is to choose u and du, to substitute it in the original integral so that it only involves u, and then we evaluate it by some known formula, right? The end result is get to that known formula and then work that problem out. Okay, so if it helps you to see an outline of what to do, that's what you're supposed to do. Let's look at the first problem. Okay, so here it is, and I guess I thought, well, why not? How about this? I haven't told anybody, through the videos at least, what the point is behind doing integrals. Like, say we do this problem, we'll find the antiderivative. What's the point of that? Well, it turns out the point of it's a long story, but I can tell you a little bit. So my grandfather, he was an aerospace engineer, and he gave me a lot of his old books. And so this is a very old book about mechanical vibrations. And if I open it up, it's not hard to see that, you know, there's an integral right there, okay? That's the kind of thing that we're learning how to do. If you ever applied this to anything, well, it's very difficult, but, you know, here's a book on mechanical vibrations, and there's a technique that uses what we're learning right now to solve some problem about the energy contained in a spring that's compressed, okay? Anyway, okay, so yes, there is a point to it. The story about how you use these is a little bit complicated, but in further videos in the future, we'll figure it out. For now, let's focus on how to do this, okay? All right, so what was the technique, right? What was the technique? That you choose u and calculate du and then substitute. So here's what I think with this one, all right? I think that we'll choose u to be, hold on a second, all right. We'll choose u to be 3 minus 2x squared. All right, and what's the reason for that? Well, there's different ways that a person could understand this, but one reason is that if I chose this to be u, what's the du? Isn't the du negative 4x? Well, that's this. So one technique that I talked about in my last video is that you choose u such that its derivative appears elsewhere in the problem, and then you'll have u and du. Another way to do this is you think about how it would reduce. Like, how do you think you could simplify this problem? All right. For this one, I think, well, here's what it will become if my substitution is made correctly. I think we could reduce this to u to the 1/3 power du. And if I can get it to that point, then I'll work it from there. That's a fairly easy problem to do. There's a formula for working this problem right there. I think we can turn this one into that by this substitution. So those are the two ways that you can think about how to choose u. So sure, I'll choose u to be 3 minus 2x squared. Sure enough, if I then calculate du, that will be negative 4x dx. That is also right there. So it's like everything falls into place with this problem. I'm not saying every problem is so easy that everything just falls into place, but with this one it does, okay? All right, so that's my choice, all right? And right here in this step, I'll make those substitutions. And while I do that, let me also write this cube root as the 1/3 power, because they're the same thing, aren't they? So let's see, if I do that, this will be, so 3 minus 2x squared to the 1/3 power, that will be u. Okay, so I'll get u in there, 1/3 power, that's this part, negative 4x dx, okay, negative 4x dx, that's equal to du, so I'll get like so. And yes, in one step I get that, all right? What do we do with this? Well, the formula for this is we add 1 to the power, and we divide by whatever that number is. So it's going to be u to the 1/3 plus 1, okay? Down here, 1/3 plus 1. And we add our constant of integration. This turns out to be, so what's that number? 4/3 up there. U to the 4/3 power, and then this is also 4/3 plus c. So here's what we'll get. Let's do 3/4 dividing by 4/3. That's multiplying by 3/4. So I'm going to write 3/4 u, but now I'm putting my answer in terms of the variable I started with. U is 3 minus 2x squared, so 3 minus 2x squared, okay, to the 4/3 power plus c. Okay, and that is, you know, in the big picture, a fairly easy u substitution problem. All right, now here, like, probably, like, no matter how much I talk about this, it will just come down to you practicing it. All right, so let's do more. This video, I'm just going to do problems. All right, what about this one? So first of all, I'll do a little rewriting. Let's do 9x, and that's written in the denominator. I want to see that exponent there. I want to see it like I've got something to a power, all right, because that's the way our rules are expressed. So I'm going to do 4 minus x squared to the negative 3 power dx. All right, so that's what I get. How are you going to choose u? Well, two ways I can look at it. If I let that part be u, what's the du? What's the derivative of 4 minus x squared? It's negative 2x. That's 9x, but I can fix the constants, okay? All right, now I said I would just do problems, and that's really my objective, but there are strategies, and it would be bad, it would be irresponsible if I ignored the strategies, but you can choose u so that a multiple of its derivative appears somewhere else in the problem. So if, you know, that's u, then its derivative is there times 9, all right? So I think that'll work. Another way you can look at it is you can choose u so that the goal of obtaining one of these known formulas, or any known formula, actually happens, all right? So somebody might say, hey, I think this problem, if we choose our u correctly, will become this. Like if I choose u to be 4 minus x squared, it'll probably turn into that, and then I'll know how to work it, all right? So let's do that. Let's choose this part in here to be u. So we'll let u be 4 minus x squared. Okay? As a result, du will be negative 2x dx. All right. Now, I'll do a little rearranging at this point. Okay? That 9, that constant, if I want to, I'm free to factor that out like so. And then I'll copy that, and then I'll put the x with the dx. Okay. So can we get those to fit up there? Remember, the objective ultimately is to get these to fit. So I see 4 minus x squared right there. I can put u for that, okay? And then x dx, well, this is negative 2x dx. That's x dx. So they're not the same. I can't substitute this up there, but that's what I want. So I'll just do this. Remember, this can be treated like an algebraic equation. You could take both sides of this and multiply by negative 1/2 or divide both sides by negative 2, however you see it. If you do that, you'll get negative du over 2 is equal to x dx. And that does fit. Now, so everything has a place now. 4 minus x squared, that's u. And then x dx, that's negative 2, negative du over 2. They both fit. So between this and this step right here, here's what I'll get, 9. Okay, 4 minus x squared, that's u. I get u to the minus 3 power. X dx, that's negative du over 2. Okay? Now from here, this negative du over 2, that is a number, that's a constant of 1/2, of negative 1/2. And in an integral, I can always remove constant factors. Like that 9 there, that's 9 times x. I can remove the 9. Now it's 9 times this indefinite integral. Same thing here with this negative 1/2. That's like u to the minus 3 power times negative 1/2 times du. I can remove that. If I do that, I'll have a 9 times negative 1/2. I'll have negative 9 over 2. So I get negative 9 over 2, u to the minus 3 power du. Now, at that point right there, I have a formula for that. Here's how you do this kind of problem. You add 1 to the power, and then you divide by whatever you get. It's at this point that the substitution was made. The original problem was transformed to be entirely in terms of u. We substituted u and du. U is the only variable there now. And with some rearranging of the constants, I have a formula for it. So our answer, negative 9 over 2. U, I add 1 to that power, I'll get a negative 2 if I do that. I divide by that same number, I'll get a negative 2 down there. My final answer, we're going to get positive 9 and 4. 9 on top, 4 on the bottom. 2 negatives makes it a positive. That I'll put down here. What was the u? The u was 4 minus x squared. With that exponent of negative 2, I'm going to have 4 minus x squared squared. 9 over 4 times 4 minus x squared plus c. Okay? All right. I got that one. This one was harder than that one, but the thought process is the same. Okay? Now let's just keep trying it. Let me see. Okay, so let's do this one. All right. Well, what do you think about this one? How would you do this? Substitute what? You're going to substitute, you're going to choose u to be something, but what? Should u be 1 plus 6 over t? Should it be that? Or should u be 6 over t squared? Or what? What should it be? Well, all right, remember, here's the motivating factor in all this. There's, how do you choose u? Well, by lots of practice, maybe you're just naturally smart and you just know. You can choose u such that a multiple of its derivative is somewhere else in the integrand, or you can choose u so that you end up with some formula that you know already. So I could look at this one like this. I could say, if that's u, this is the du, right? What's the derivative of 1 plus 6 over t? It's negative 6 over t squared. So I think that's what we should do. If that's u, there's its derivative. Another way somebody could look at it, though, right? Because I'm saying that you can choose u so that its derivative appears somewhere else in the integrand, or you can choose u so that you get some formula that you know already and that you're familiar with. So somebody could say, like, I think this will become the antiderivative or the indefinite integral of u to the third power du. Okay? Now, either way, no matter how you think of it, that motivates this to be the u. All right? So 1 plus 6 over t. That's what we'll choose. If we choose that, what's du? Well, the derivative of 1 plus 6 over t is negative 6 over t squared dt. All right. Now, do both of those have a place up there? Because these are substitutions. The objective is to take this, u is the same thing as 1 plus 6 over t, and substitute it up there somewhere. So sure, I could put u right there. U is 1 plus 6 over t. Is there a place for du? Du is negative 6 over t squared dt. I don't see negative 6 over t squared dt. It's not there. That's not negative. So what do we do? Remember, I said before with other problems that we can treat this algebraically if we need to. If I need to modify this so that it does substitute up here, then I can add the same thing to both sides or subtract or multiply or divide. And if I multiply both sides of this by negative 1, I'll get this the way that I need to. It will say negative du equals positive 6 over t squared dt. So this and this both have a place up there. That's the goal, all right? If I do that, I'll get this, okay? So in this step right here, the substitutions that you see there that have been circled, I will make those. So 1 plus 6 over t, that's u, so this is going to be u to the third power, okay? And then 6 over t squared dt, that's negative du, okay? Now, when you look at this, is that subtraction? I put this in parentheses because I didn't want you to think that's subtraction. Where'd that negative come from? That dash right there. That's a factor of negative 1. You know, these are multiplied together to start with. This is 1 plus 6 over t to the third power times 6 over t squared times dt. This is multiplication. This reads like u to the third power times negative 1 times du. So if it would help you to see it that way, then see it that way. It's a factor of negative 1. What do we do with constants? Like if I have a constant factor in an integral. Well, I told you in another video, I know it's a lot of information, but that's how math is, all right? That if you have an indefinite integral with a constant times something, you could factor it out. So that negative 1 right there, we can factor it out. And we'll get negative 1 times u to the third power du. And we know how to do that one. This is easily done as this. Let's see, carry down the negative, u to the fourth power over 4 plus c. Okay? My final answer, in order to put this back in terms of that variable t that I started with, u, after all, is equal to the same thing as 1 plus 6 over t, so I'll get negative 1 plus 6 over t to the fourth power over 4 plus c. And there's our answer. Okay. So, all right, we got that one. Let's just doing examples, all right? What about this one? Okay, 1 over root 6x. Let's do this to start with before I start thinking about how I'm going to do it. Would this be the same thing as this? Those are the same thing. What kind of problem do you think that would be? What could u-substitution make this become? Maybe, I think if we make the substitution correctly, we'll get this. Say we did that, will we be able to work it? Yeah, that problem is workable. There's a formula for doing that. What should you choose for u to make this become that? All right, let's be u is equal to 6x. Yeah, that substitution, we'll turn this into this. That's the objective, all right? Is ultimately, this has to become something we know how to do. I think that's what it could become. So u is 6x. All right, what's du? 6 dx. Derivative of 6x is 6. Does this fit up there? And that. See, I got u. Du is 6dx. Does that say 6dx? No, we're missing the 6. So, all right, well, you know what I'm going to say now. We'll take this. We'll multiply both sides by 1 over 6. Or another way to look at it, you divide both sides by 6. But that both of those are allowed. You can treat this like an algebraic equation as far as that goes. And so we'll say du over 6 is equal to dx. Okay, this and this, they fit. They work. All right, so here goes. Right here, we will get u to the minus 1/2 power. Okay, and then dx is going to be du over 6. Okay, what about that over 6 part? What is that number? That's a 1 over 6. So we can factor out a 1 over 6. This is like 1 over 6 times du. This is like u to the minus 1/2 power times 1 over 6 times du. We can factor out the 1 over 6. That's one of the things we're allowed to do. And so we get this. Yeah, and that problem we can work. Right? What do? How do you work that? Carry this down. Okay. Add 1 to that. Negative 1/2 plus 1 is 1/2. And divide by that same number. So like kind of like that. All right. And then this is 1 over 6 how do you divide by 1/2? You multiply by 2. How do you divide by 1 over 2? You multiply by 2 over 1. And then u is what? U is 6x. Okay, so what is this? 1/3, 2 and 6, reduced to 1/3, root 6x plus c. Okay. There you go. All right, so another one down. Let's do these two that involve sine. Okay. All right. Now, what should we choose u to be? Remember, part of what we're learning when we do this is we're going to figure out what should that be. Well, here there's not a whole lot to choose from. Probably say u is 5x. Why would you say u is 5x? Well, because I think this will become one of my formulas that I have. All right. One of the objectives, one of the methods for doing this, one of the methods for choosing the u, how do we decide what u should be, is we choose u in a way that it transforms the problem we have into something we know how to do. So I think if we choose u correctly, we could transform this one into sine u du. Okay, what's the antiderivative of sine u du? It's negative cosine u plus c. All right. So I think this one with the right choice there can become sine u du, and then that one is answerable. We know how to do that one. So let's let u be 5x if we do that. Okay, so we chose u. What's du? Du is 5dx. Okay. All right. Now, as I do these, I'm like trying to emphasize, like consistently emphasize some of the same things. But here's the outline of our method. How do you do u substitution? You choose a substitution, u being some formula that involves x. Then you calculate du to be equal to f prime x dx. Both of those then are substituted after that. So if I choose u to be 5x, the derivative of 5x is 5. Du is 5 dx. All right, well, okay. So at this point, hopefully it's getting a little bit predictable. This fits. Okay, put that right up there. This does not. Okay, so let's divide both sides of this by 5. And then those both fit, right? 5x will be u, dx will be du over 5. My goal, whenever I choose and formulate my u substitution, is to transform this problem to be entirely in terms of u. I can substitute the x and the dx away now with both of these. So we'll get sine of u, 5x being u, dx is du over 5. What is that du over 5? Well, you can think of that as 1/5 times du. It's the same thing. So there's a constant of 1/5 in here, which we then factor out 1/5 sine u du. And then this is a known formula. It's just a matter of fact that the antiderivative of sine u du is negative cosine u plus c. So we'll carry down this 1/5. This part, negative cosine u. And then always we add our constant of integration at the end. Final answer, let's see. Negative 1/5 cosine, what was u? 5x, okay, plus c. All right, there is our answer. Okay, another one down. I want to do two problems that involve sine that are ultimately the same formula, but that look very different from the beginning, okay? So like this one and this one, this one looks more complicated than that one. This one looks like it might be harder. And the substitution is different between them too, but they end up at the same place, all right? So I thought I'd show you another one to emphasize that about this. All right, now, so again, I think this one will be this. Okay, so I can choose u to be 2 over theta. Theta is the variable in our problem to start with. You know, that's all right. That's one way you can do it. That's one way you can decide u. You can choose u to be that 2 over theta because you think it will end up being sine u du. You think it's going to be that kind of problem. What's the other way to think about it? How do we choose u? How do we decide? Oh, I've been showing this slide. How do we choose what u should be? Well, I felt silly. Oh well. How do we choose what u should be? Okay, so choose u so that you get some formula that you know and that you're familiar with. Or choose u, I mean there's two basically equivalent strategies. Choose u such that a multiple of its derivative appears somewhere else in the problem. All right, so if I choose u to be 2 over theta, what's that derivative of 2 over theta? Is it 5 over theta squared? Well, it's not 5 over theta squared, but it's pretty close to that. With the exception of the constant being there, it's basically going to be that. So look, if I choose u to be 2 over theta, du is negative 2 over theta squared d theta. Okay, so that's 5 over theta squared, but we can deal with the constants. Here's what I mean. So let's do a few things at once. That's a 5, right? That's a constant factor of 5. I'm going to remove that. And I'm going to do some rearranging here. So that's gone. And I get sine of 2 over theta. Okay. And then that would leave me 1 over theta squared d theta. Okay, so I took that 5 out. I left this in there. Only constants are factored out of indefinite intervals. You can't factor out the theta or the variable, whatever the variable is. And I say, well, I almost got it, right? So there's u, 2 over theta, so that's going to be sine u. What about this? Is that the du? That says 1 over theta squared d theta. This is not 1 over theta squared d theta. It doesn't match that. I got this negative 2, but that's okay, right? Because we can take this, and with the goal of getting it to match that so we can substitute it, I'll multiply both sides by negative 1/2. If I do that, this equation becomes negative du over 2 on the left-hand side. On the right-hand side, it becomes 1 over theta squared d theta, right? We're going to cancel the negative 2 and introduce it on this side. Now, so I did that. Do you see, as a result of that, both of these have a place up there. Both of them can be substituted. I can change this integral from being in terms of theta to being in terms of this other variable u, and it being, as a result, simpler and easier to work. That's the goal of the substitution, to make the problem simple enough that we know how to work it. Because unless you just know the answer looking at that, which maybe you do, but unless you are that person, then we have to reduce it to something different. Okay, so if in this step right here, I make those substitutions, I'll get sine u, 2 over theta being u, 1 over theta squared d theta is negative du over 2. Okay, so all right, here goes. I'll take that number out because I don't quite have it all the way reduced to sine u du. That number right there is negative 1/2 du. There is a factor of negative 1/2 right there. It's a constant. Constants can be removed from the integral. I remove the constant. I'm left with this. That is a known formula whose answer is negative cosine, right? Just like it was up here. Exactly like it was right there. Okay, we get to the same place. The substitution was a little bit different to get us there, though. So we get negative 1/2. Antiderivative of sine u is negative cosine u, and then plus c. Final answer. Let's see. Negative and negative. I'll get 1/2. And then I got cosine. U from the beginning was chosen to be 2 over theta, so we'll put that in. This will give us our answer in terms of the variable that we started with, which was theta, and then plus c. Okay. All right. So every problem I've done so far is technically different, but they're all, the method, I mean, with every time, I think the method is so much alike, okay? And I'm just doing the problems over and over like this so you get used to it and you see what's in common. All right. Because ultimately, how do you know what u should be? How do you choose what u should be when you're doing this? Well, I wrote these methods down, but I mean, ultimately, it might just be by practice. You might only fully understand these after you practice a lot more. But nonetheless, I did tell you about them. Let's do one more thing before I move on. So this, it's just worth emphasizing this. I want you to know this. I want you to know what makes this the right answer. Is it because I did all this right? Not really. What makes this the right answer to that is that if I take the derivative of this, then I should get that. Okay? And oh my goodness, I am having an off day. See that 5? I forgot about the 5. Okay. 5. 5. 5. Okay, so that's what it should be, 5 over 2. All right, I realized that as I was telling you, I was checking it, I was thinking about it in my head, checking it, realized, oh, I'm going to need a 5. But yes, okay, what makes that right? If you take the derivative of this, you should get that, okay? So, all right, anybody who learns this, like when they're first learning it, I mean, if I was taking it seriously and really trying to get good at this, I would check every problem that I did, all right? So what's the derivative with respect to theta of the constant 5 over 2 times cosine 2 over theta plus c? What is the derivative of that? Okay, well, so we carry that constant 5 over 2 down. The derivative of cosine is minus sine . Okay. So derivative of cosine 2 theta is minus sine 2 theta. Then to complete the chain rule on this, I have to say times the derivative of 2 over theta. That's negative 2 over theta squared. Okay. And then plus what's the derivative of c, capital C right there? That's a constant. So that would be 0. What does this turn out to be? Okay, well, so I've got two negatives that cancel to be a positive. The 2's cancel. I have a 5 on top, a theta squared on the bottom, so I'll get 5 on top, theta squared on the bottom, and then times sine of 2 theta, or sine of 2 over theta. And that is what I started with, 5 over theta squared sine 2 over theta. All right, maybe when I check it, I mean, this is the way I think about it. Hopefully you'll try to think about this in the same way. But I kind of see like how that part and this part have a lot to do with each other. Okay? When we choose this correctly, it should also see how it unfolds when we check our answer. And if you can see it that way, if you can see when I check this answer by the chain rule, that this part unfolds into that one and so on, then it will make choosing this and understanding and being able to make your choice reliably and quickly will make that easier. All right? That's why occasionally I want to check an answer and show you.